PauliExclusion. This is one of the things that everyone grasps onto. Spin up, spin down per orbital. If you've got multiple orbitals, you are restricted to spin up, spin down in each of those orbitals. Okay, so the goal of what I'm going to do is I'm going to explain how you can read Atkins and give you some understanding of the notation that he gives. So Pauli's exclusion principle is a subset of the Pauli principle. And the Pauli principle, let me give you some background. So we know H psi equals E psi. So Pauli and Sommerfeld are sitting around at the Bohr Institute in Copenhagen, and they're trying to figure out what is, so the atomic emission spectrum that you'd get from certain elements was a little weird. In particular, you'd have like the helium line, you'd have two lines that were really, really close together. The spectral separation between these, so the delta E between them, was smaller than the delta E you'd have from the M sub L1 to the M sub L2. So if you get R theta phi and L M sub L, you have L or N, L, and M sub L. You have these quantum numbers that originate from which wave function satisfy the Schrodinger equation. Okay, there's 3 quantum numbers, but each of these give you different energy states, different E. The difference between those energy states they saw in the atomic spectra did not match. They were too close together. There was something causing the slight splitting of the atomic lines, and they didn't know why. So what they did was they went to their friend Stern-Gerlach, who said that there's going to be some sort of additional information associated with electrons in the, just inherent to the electrons, spin. Cool. Notice how there's no spin quantum number here. So getting Stern-Gerlach's experiment to blend with wave mechanics and to explain some of the nuances of the splitting of the spectral lines, they needed another quantum number to do that. And so need another quantum number. The problem is this one is not restricted to boundary conditions. These all originate from boundary conditions and the potential energy associated with the Hamiltonian. This one does not. It's intrinsic to the electron. So, and this we know from the previous video, we have plus or minus spin a half. And so how do you incorporate that? That's where Pauli's principle comes in. He says that, so this is the Pauli principle. He says that okay, so if you have a, first of all, this is for fermions. When you have psi, let me see if I get the notation right, psi of electron 2 and 1, if you flip these two such that you have psi of 1 and 2, so you have 2 electrons, I'm going to say red electron and black electron. If you exchange those two such that the black one then becomes the red one becomes the place of the black one, they don't have spin up and spin down yet. If you exchange those two, assuming that they're distinguishable, that's a whole other story about indistinguishable versus distinguishable. Can you tell the difference between the 2 markers? Or if I have, can you tell the difference between the 2 markers, assuming that the cap was on? So yes, you can, but assume that they're indistinguishable. Okay, if you flip the 2, for fermions, if you do that, the wave function that describes this system has to be the negative of the wave function that describes this system. That's it. There has to be a negative sign. Cool. And it says, when the labels of any 2 identical fermions are exchanged, and identical meaning that, so N, L, M sub L, if these are the same, then they are identical fermions. when the labels of any two identical fermions are exchanged, the total wave function changes sign. And that's the total wave function as in the big phi that then equals all the little hydrogenic atom wave functions based off the orbital approximation. And what's cool is the difference between that and bosons, which are integer spin. The Pauli principle is when the labels of any two identical bosons are exchanged, the sign of the total wave function remains the same. Go team. Okay, so what does that mean? So this means that, I lost my black marker. We need a way to check that, so need way to check that psi represents the system. Because before, we would guess, not really guess, I mean, there was a lot of thought that went behind it, but we would say, okay, if I know my atomic energies from the spectrum, or at least I know my delta E, and from that I can pick out what E1 and E2 would be. I have a Hamiltonian that operates on the wave function, and then I get that wave function back again, and you would do only one wave function would satisfy this equation for the particular energies. Okay, now the problem is this would give you an N, L, and M sub L only, but you need a way to pick out an M sub S. So once you find your wave function, there's another step now to verify that it is in fact a good wave function that satisfies boundary conditions, which gives you these, but also satisfies the Pauli principle. Cool? And that's that if you exchange any two electrons, you're going to get a negative wave function. Okay? So the way that that's represented is by, oops, let me grab my notes. You can tell how prepared I am. Sorry, oh no, wrong page, no. I'm missing page 10. Pause, so sorry. Go team, it has been found. So what I wanna do is I wanna talk about how we get psi 2,1 equal to minus psi 1,2. And the notation in Atkins, and hopefully that'll help clarify what the sigma value is. Okay, so you have two electrons, and they can either be spin up, spin up, spin up, or spin down, spin down, spin up, spin down, spin down, spin up. Okay, so you've got four combinations. Of those four combinations, there's only three of them that will work, that will give you a negative. And so the way that they represent this is so this would be electron 1, this is electron 2, 1, 2, 1, 2, 1, 2. Okay, so the way it's represented is this is alpha. So alpha means spin up. Alpha equals spin up. Beta equals spin down. Okay, so this is alpha 1, alpha 2. So electron 1 has alpha spin up. Electron 2 has alpha spin up. This is beta 1, beta 2. This is alpha 1, beta 2. This is beta 1, alpha 2. Cool? All right. The kicker, though, is that, so what you would do is then you would say, all right, so I've got the total wave function is the product of the orbital part and the spin part. So the orbital part is the R spherical harmonic. There's going to be an additional part such that the total wave function also takes into account the spins. Cool. So that would be so psi 1. So this is the hydrogenic atom for electron 1. Psi 2 hydrogenic wave function for hydrogenic wave function for psi 1, hydrogenic wave function for psi 2 times alpha 1, alpha 2. So that's just the wave function for that combination. Then you have the same thing, psi 1, electron 1, the wave function for electron 2, and again, this is going to be R1, spherical harmonic. Cool. And then same thing here. This would be for the second one, just to give you some context. And then you've got beta 1, beta 2. Cool. Then we get into these. These are a little harder. These originate from a linear combination of the atomic orbitals. And this is where the 11th edition and the 9th edition diverge quite a bit. 9th edition goes in deep. 11th edition just drizzles a little bit of this. Bear with me as I explain the notation. So you're going to have a linear combination such that psi 1, psi 2 multiplied by sigma plus of alpha of 1, 2, and then psi 1, psi 2, alpha negative 1, 2. I think that's the right. Okay, cool. These two represent those two states. Go team. So you have 4 combinations, 4 possible wave functions. Only a few of them are going to work and satisfy H psi equals E psi with this additional spin information. Okay, so let me explain what psi 1, 2 is. So psi, oops, sorry, sigma, goodness. Sigma plus 1, 2 equals normalization constant, because this is a wave function also, alpha 1 beta 2 plus alpha 2 beta 1. Cool. So you've now got a combination of, you can't tell the difference of which one's up and which one's down. You know that one of the electrons is spin up, but you don't know which one. Okay, so since you know that one of the electrons is spin up and the other one is spin down, the question is, well, which one is which? So you take both into account and you do a linear combination, which basically you add it together, the two wave functions that could represent it. Those are those two possibilities, okay? But these are waves. So for every constructive interference that you have, you also have a destructive interference component, which means that you've got the same thing with the negative sign now, 1 over 2, 1/2, alpha 1, beta 2. Any guesses what the negative is going to do? Alpha 2, beta 1. Okay, that's what this sigma is. It's the result of a linear combination of the fact that you don't know which one is spin up and spin down. Cool. Okay. I don't want to use the phrase, do you need to know this? Because that makes me think that this isn't important. It is important, but for what we're using, this is about an appreciation for where Pauli's exclusion principle comes from. Spin up, spin down in one orbital. You can't have spin up, spin down, spin down. You have to have one or the other in a single orbital. Okay. So it turns out that if you have them paired like this, those two, when you exchange the two, yield a negative wave function. That's it. We want to make sure that if you change these two, you get a negative sign. The only way you do that is if these two are the solutions to the Schrodinger equation. These two, so this one and this one. And under that circumstance, you can then have, the negative sign. Cool.